Welcome, everybody. My name's Daniel. I'm also here with Ryan and Luke. We are going to be talking about processing and threading on Mac, Windows, and Linux. We're going to start here with the Mac OS. The Mac OS is broken into several different layers. We have the kernel and device drivers, core OS, core services, media, and finally the Cocoa application layer. These are kind of the layers of abstraction that Mac uses for its operating system. So the kernel is based on Mach microkernel architecture, which was developed by Cambridge. It's a preemptive multitasking operating microkernel architecture. The processes are shared with the CPU efficiently, watching over the computer's processors, prioritizing tasks, making sure activity levels are at the maximum, and ensuring that every task gets the resource it needs. It uses criteria to decide how important tasks are, and therefore how much time to allocate to it before giving to another task its turn. Processes are not dependent on another process, yielding its processing time, so it is preemptive. It is also based on BSD architecture named Darwin by Apple. It is an open source operating system, and also it has processing scheduling done by a priority queue. The priority queue is broken into a couple different layers. We have normal priority. We have the system high priority, which is obviously raised above normal. We have the kernel mode only, reserved for kernel threads or higher. And then finally, real-time threads. So these are based on well-defined threads that need a fraction of total clock time, regardless of other activities, such as audio players or media players. So the threading on the Mac OS is done a couple different ways. The first is through POSIX threads. These are C-based interfaced threads for creating basically threads inside of processes. We also have the method of creating those threads in those kind of code fragments there, the pthread_create. You'd actually create a method and then call that method to create it. And then you would also have to tell it when to start that thread. And then there's even setting the schedule parameters where you can set actual specific scheduling for your own threads, like first in, first out, and round robin. This is kind of a base underlying thread creation of Unix-based systems. Then we have Cocoa threads. Cocoa threads are basically NS threads set. They allow you to set their priority from 0 to 1, basically with 1 being the highest. Cocoa threads are proprietary to Apple. They were developed as their early implementation of threading. And both Cocoa threads and POSIX threading use mutexing and conditional locking methods. So these are kind of the ways that Cocoa and POSIX make sure that they do not get into race conditions. One other thing to note with these types of threading is they each take about anywhere from 1 megabyte to 8 megabytes in size, and they require approximately 90 microseconds to set up. So threading is not an inexpensive process. So Apple developed a new technology that they wanted to replace threads with. And this is why they actually don't recommend using POSIX or Cocoa threads unless you absolutely have to, because Apple developed a thing called the Grand Central Dispatch. Grand Central Dispatch lives in the core services. It's the recommended method for basically threading. It's an API that allows for concurrent and asynchronous scheduling. The cool thing about it is you just write inside your application or methods a wrapper that says calls the Grand Central Dispatch to execute a piece of your method concurrently or asynchronously, and it will actually kind of adjust it to the architecture of the machine. So if you have a dual core processor, it will use as many of those processors as possible. If it has a quad core, 8 core, 16 core, 64 core, however many processors there are, Grand Central Dispatch automatically determines what's the best way to thread that piece of your process. So it is the recommended way to handle multi-threading on a Mac. And it, like it says, handles multiple processors. So that's kind of the major methodology that Apple uses on their Mac OS operating systems for scheduling. We are now going to go ahead here and move over to Windows with Luke, and he's going to walk us through the Windows architecture.
Thank you, Daniel, for passing it off to me. I'll go ahead and talk about Windows, and we'll be going over how they handle processing, threading, and scheduling. So Windows has a processing hierarchy that is controlled by their job manager or by their process manager. There's a process manager within Windows that has this hierarchy set up, and there are two layers that are abstract and unique to Windows that Windows does. The first one is job. There are jobs, and jobs contain processes in this hierarchy. And these processes, as you know, contain multiple threads. A job can contain multiple processes, and processes can contain multiple threads. But there's also another layer that is an abstract for Windows that Windows uses, and that is fibers. Fibers do not specifically belong to threads. However, they are available for the operating system to use and the process manager to use in order to perform smaller functions of threads. And it results in lower overhead, and it takes less time to create and delete these fibers as opposed to using threads. Going down this entire list, you go from higher amounts of overhead and longer times for switching between each part of this hierarchy to lower amounts of overhead down at the bottom with fibers and less time switching in between fibers and different fibers for different threads. And for threading, there are lots of unique features that Windows provides for threading. Daniel mentioned a lot of things that are pretty unique to Mac, along with Grand Central Dispatch and what they've been doing. Windows hasn't had their own specific way of making processes threaded on its own without having to program that in. However, they've included features to improve the flow that threading has overall in their operating system. Windows has thread pools as a start. And what this means is that instead of having threads sit around, or instead of having threads be created and deleted every time that they are used and made for each specific job, once they complete their job, they will go ahead and grab another part of the process and essentially take on that thread, that part of the process. That way, it removes the overhead needed to create and delete threads, which is quite a bit. Um, and one thing that they've added that I'll be talking a little bit more about later on in scheduling is they've made it so that each thread has a user level thread and a kernel level thread. And what this basically allows for is it allows for switching when threads are waiting on IO, like we talked about in class before. If a thread is in user level and waiting on IO, it can't continue to perform other threads within the process. However, if it's in the kernel level, it can, but it takes a long time to switch between user level and kernel level. So they made every single thread have both that stay in their respective areas. And when you match this with pooling, with the thread pools that there are, it makes it so that there's very little overhead when you switch between threads that each process is running. Another function that Windows has added is the non-uniform memory access function, which is NUMA, out here. And what that does is there's a part of the operating system that keeps track of what memory is on what local cache on which processor. And if you're doing processes or threads or fibers that have to do with the same cache and the same memory that the last thread used, that would still theoretically be on that cache, it would be more efficient to have the next thread that uses that same memory be on that same processor because the cache is already there and it skips all that loading. And so they have some sort of process that goes and determines what the ideal processor is for each thread and each fiber. So that way, it can reduce wait time on memory when switching in between the threads. So I'm going to go ahead and move on to scheduling now. And here is a general overview of how Windows does scheduling. There is a large table that was given out by the book that outlines the rates or the levels of priority on certain functions and threads and processes. And so, as you can see, on the left side of this table, we have the thread priorities, which are automatically set by the machine. The machine is able to set all these, and it is hard for a user to change these. However, if you've ever played around with the Control-Delete Task Manager on Windows and you've gone to your processes and you've right-clicked them, you can see that you can set process priorities within Windows. And so these are able to be changed by the user on the upper row. And with a mix of these two, the processes that you can change and the process priorities that you can change and the thread priorities that are set by the operating system, you can change what priority the process may have in the scheduling system. For if you set any process in real time, one thing that you can notice here is that any process that I set in real time is automatically going to be preferred over any other process when available, even if it's set to idle by the operating system in the thread priorities. And everything other than that will go in a descending order based on what you set it as. So the scheduling system has each process have a value between 0 and 32, or 0 and 31, 32 total values. And how it schedules things is it bases it on a first priority system. So the highest number is going to get the most amount of time and is going to be put first and scheduled first. And then it descends down the list. However, if you have more than one priority that is equal when you get down to the bottom of all your cores that you can schedule, or bottom of all your processes that you can schedule, it goes ahead and it uses a round robin system, giving each one a specific amount of time to run the process before it switches to the next process of the same priority. And it continues downwards as it goes. One thing that Windows has included is that there's an auto boost value that is added to certain processes that need input from IO or need to interrupt the system somehow. And the auto boost value can be, I believe, anywhere from 0 to 10, as was given by examples in the book. Audio was one of the highest ones because that is one of the most noticeable differences if that's not scheduled immediately. And so, as I was talking about, since Windows 7 onward, as I was talking about before with each thread having user threads and kernel threads, there was user mode scheduling that was implemented, which is essentially it being able to switch between running that user thread or that kernel thread in between, or when you're interrupting the system for an interrupt for IO or whatever it may be. And this saves overhead of moving all the threads into kernel mode when you need to, and all the threads out of kernel mode when you need to. And that's going to be it for me. I'm going to go pass it off to Ryan, who's going to be talking about Linux.
Okay, thank you, Luke. Yeah, I want to be talking about Linux, the processing, threading, and scheduling. So first off, Linux was built by programmers, and it's for programs to use in complex software development environments. And so the layers of Linux, at the top there you have users, you have your standard utility programs, your standard libraries, and then at the Linux OS, this is where the process management happens, and the memory management, the file systems, and the IO. This is also where the kernel mode is. And then at the bottom, that's where the hardware is. So within the kernel, you have the kernel structure, and it contains a process management component. And this is where the signal handling happens. And then the most important part of it is the process thread creation and deletion. And then also this is where your CPU scheduling happens. And then as a side note, Linux treats both processes and threads as executable entities and then schedules it based on a global scheduling policy. And I'll talk more about this in the next few slides. So how does Linux does processing? So a process is kind of the main activity of a Linux system. System calls exist to create processes and threads. Some of the fundamental concepts to be aware of is Linux processes are similar to the classical sequential processes that we learned in chapter 2. Each process runs a single program and initially has a single thread of control. It also has a program counter that comes with it. And then after it's created, then you're allowed to create additional threads. Another important concept is the use of daemons or daemons, however you say it. Since Linux is a multi-programming system, you can use these daemons as background processes. And even if the user is absent, they will awake every minute to see if there's any work to be done. If not, then they'll go back to sleep. The last thing I want to talk about is the parent-child relationship in processes. So a process is created by the fork system call, and that just creates an exact copy of the original process. So when you create that, you have a parent process, and then you can create child processes from that. And if you do, each process has their own private memory image. I would say the parent and the child each have their own private memory images. So if you change variables or data on one, it will not be reflected in the other. For communication between each other, they use pipes, which we actually learned about in class. And the way they stay synced is they actually block other processes' read operations until the data that they're loading is complete. And then the second way they communicate with each other is through signals. And so if a process receives a signal, if it accepts it, then a handler will actually take over to process whatever that signal is. So let's talk about implementation. Linux kernel represents process as tasks. This is actually different from other OSs that actually make a distinction between processes and threads. Linux just calls each of those a task structure. So for example, a single threaded process will be represented with one task structure. So when creating a process, it creates a new process descriptor, which holds all the important data for a process. And then it creates a user area for the child processes. And then the children are given a PID, memory map is set up, and it's shared at the parent's files. And then its registers are set up, and then the child process is ready to run. And also, since copying memory is expensive, Linux gives their children their own page tables and has them point to the parent's pages, but only they're marked as read-only. So anyway, so as you can see, creating processes in Linux is actually pretty straightforward. So threading in Linux is different from other OSs who make it clear, as I kind of talked about, they make a clear distinction between processes and threads. But in Linux, what they did is, and this happened in 2000, they created a system called clone, and this kind of blurred the distinction between processes and threads. So classically, when a new thread was created, the original thread and the new one shared everything but the registers. But what clone did is it made it possible for each of these aspects and others to be process specific or thread specific. And that was kind of the main distinction. So if a new thread is in a current process, it shares that address space with existing threads, but every subsequent write and address space by any thread is visible to all the other threads in the process. But on the other hand, if the address space is not shared, then the new thread gets an exact copy of the address space, and then any new writes, the new thread is not visible to the old ones. So the last thing I'll talk about is scheduling in Linux. So because Linux threads are kernel threads, scheduling is based on the threads, not the processes. And then kind of the three main classes for threads is, and as you saw previously, it's kind of some of the others. You have real-time FIFO, real-time round robin. And then you also have time sharing too. But the current default in modern Linux is the completely fair schedule, is what it's called, a CFS. And the main idea behind this is to maintain balance or fairness in providing processor time to tasks. So if a time for a task is out of balance, if they give too much time to another task, then they actually rebalance and give the needed time to the others. So in the past, Linux would use a run queue for their schedulers, but when they switch over to the CFS, it actually uses a time-ordered red-black tree. And I should have added a diagram, but you know what a red-black tree looks like. It has a couple interesting properties. So the first one means it's self-balancing. So all the process will get the same amount of time allocated from the CPU. And then secondly, operations in a tree occur at O of log n time, which is very efficient for inserts and deletes. And that wraps up the Linux portion of this. And we'll move on to deadlocks.
All right. So talking about deadlocks, deadlocks are basically a really important problem to solve with processes and threads. With deadlocks, it's basically where your machine gets stuck in a condition that it cannot remove itself based upon a couple key conditions, and we will talk briefly about those. The first condition listed there is the condition of mutual exclusion. As the diagram shows there, we have two processes and one resource. Process one is currently owning resource one. Process two is requesting it, but it cannot take ownership of it because there is mutual exclusion. Resources can be only held by one process at a time. Hold and wait is another important condition for deadlocks to occur, and that is where process one is currently holding resource one. It wants resource two, but process two is holding resource two. And so process 1 is just going to sit there and wait until resource 2. And it's going to sit there, wait, and while it's waiting, it's going to hold on to that original resource. Another key piece is no preemption. And so when you hear about preemptive operating systems, like I mentioned back in the Mac OS, is that this is basically the concept that the operating system has the authority, has the power to stop a process or to remove a resource from a process. With a no preemption policy, process 1 can hold on to resource 1 as long as it wants, and the operating system has no ability to stop that. And finally, circular wait. And this is basically the complete diagram of a deadlock. We have 2 processes, each wanting both of the resources, but each both waiting for the other to release a resource. So if the resources are mutually exclusive, which is what we're having here, is that R1 and R2 can only be held by one process at a time. And we also have hold and wait, where processes just sit there and say, I'm going to hold on to this resource until I get the other one. They're not going to let go of it, thinking maybe if I let go of it, I'll get both of them later on. And then finally, the no preemption condition means that the operating system cannot come in here and fix all of this out. So you might be asking, how do we solve this problem? Well, the answer is there are a few kind of good steps. First, non-assignment, which basically means don't give processes exclusive resources if you don't have to. Try to avoid giving them resources and not assigning them. Avoid pre-assignment. Basically, don't give a process a resource until it needs it. Allow preemptive processes, being preemptive. That basically means make sure that the processes can be stopped. If the operating system decides you've had enough time with that resource, we need to let somebody else try it out. You need to make sure that those processes can be stopped. And finally, release resources. Let those resources go as quickly as possible. Do not hold on to them beyond what the time that you need them. So with these 4 are some of the ways that you can prevent deadlocks, and it is really important to build prevention into an operating system so it does not get stuck. So one final thing that we were going to do as our in-class kind of hands-on activity was we were going to do this kind of connect the dots kind of drawing. And this was going to kind of simulate how a processor, completes instructions one at a time when it's single threading. So I'm going to start it here, and you're going to kind of start seeing it drawing that with this connect the dots picture with single threaded and a single processor. And you'll see that one line is kind of being drawn throughout. Once it finishes here, what you're going to see is basically the process moving to a multi-threaded single process. Now, it might look like for half a second that it's actually drawing 2 parts at once simultaneously. But if you look closely, you'll see it's kind of jumping back and forth. And this is what multi-threading does. It allows it to look like it's doing multiple processes, but it's actually doing one at a time. And then finally, and you can even see there, it took longer, and that's due to context switching. But multi-threaded with multiprocessor, that is truly fast. You can see here it's doing both at the exact same time, so it is kind of completing this together. And there we go, a very fast execution. So hopefully this gives a kind of visual representation of what multi-threading, multi-processing, all of this, what we've talked about today, kind of culminates in, which is faster and more efficient processing. Thank you, and have a great